Now I introduce the stochastic actor-critic algorithm. For the continuous action reinforcement learning problems, policy gradient method is one of the popular techniques. To use a gradient descent method, we need to define an objective function. Based on the reinforcement learning problem solved by Markov decision process, we defined state distribution and the policy distribution. This is the state and this value function and the action state, the action value function. So once we have this objective function, then we can calculate the gradient of the object function with regard to the parameter for the policy parameter theta in this formula, and to express this integral as expectation. So we need to use this relationship and to get this one. This integral. This is the state distribution. This is the policy distribution. So we sample state from raw, we sample action from policy, then we calculate the expectation of these two variables. So if, for example, we select one state from the state distribution row, we search for the policy pi, and the policy pi we select A. If we know the Q, we can calculate, we can evaluate this policy is good or not. However, this Q is not only depend on the policy or the action selected from A also, because this is a cumulative reward. So they depend on the whole trajectory. If in some case, special case, we may calculate this true value after we select the A to evaluate pi. But if the action, if the policy is a stochastic policy, that means we don't know what's the action we select in the next steps. So we no way to know this true value function. Right now, we just for the stochastic policy, see how can we use we actor-critic method to search for the optimal policy. Because this, just a search for the policy, we defined this part as an actor. This part, this uses the Q function to evaluate the policy. We call this critic. As we said, because for the stochastic policy, we cannot know exactly the true Q pi function in gradient of the objective function. So to do so, we need to find a way to approximate of this part, to approximate this Q pi. For example, we use the approximator QW, use QW to replace Q pi in this form, in this gradient. If we can get QW, then we can evaluate the actor, or that is we can evaluate performance of the policy. As we mentioned, since the true Q function is depends on the whole trajectory, so for the stochastic policy, we cannot know the true Q pi value. That's why we try to find a way to calculate the QW here. Usually, if we use QW to replace the Q pi, we will have a larger bias. To reduce the bias, we use, let the function approximator QW is satisfied with two conditions. One is this linear function of W. This is the factor of the W. That means this is a linear relationship with the W. Second, the W should be selected to minimize the mean squared error. That means that this approximator closer to the true value on this distribution and the policy distribution. In that case, then we use the approximator to replace the true Q value function. We don't have the bias. Without the bias, it means the distribution of the QW have the same mean with the true Q value pi function distribution. However, if Q we select satisfies the two conditions, that means we seems like all equal to don't have a critic part at all, just like the enforce method. For more detail, please check with this reference. Thank you.